Welcome back to Material Atomics. I'm Michael Shiloh.
I'm Anastasia.
Today we're going to try something a little bit different. We're going to open up our conversations channel to a third party. And today we have Jeff Yee, a garage physicist, is that fair to say? Who's been thinking his whole life really about the structure of the nucleus. And this is a really important topic here on the channel, which we haven't opened up yet. We've been dealing with the motion of the surface of the atom, the electron, if you will. And now we need to start thinking about what's going on at the nucleus, because our model has a shell which actually involutes in order to provide for the spin 1/2 motion necessary in electricity and magnetism. But what's happening inside of the vortex, right? What's happening at the center of the atom? What's the shape of the structures? Why do they have the energetics that they do?
Not only that, but how does this structure at the heart of the atom inform the orbital shapes and dynamics of the outer shell of the atom?
And that's what I think Jeff really brings to the table, is he's thought about how the nucleus informs the shell structure itself. So let us know what you think. Tell us if you like this format, and give us your ideas in the comment section. Come hang out on Discord. And yeah, sit back, enjoy.
In undergrad for mechanical engineering, you have to take a lot of electrical engineering classes as well. And so the study of electronics. And I just remember sitting there thinking in college, here's a list of equations that we have for electronics. Here's a list of equations that we have for mechanical systems. And look at how similar a lot of these equations are. Right? You can repeat something equals something times something. Right? Classical F equals ma, or in electronics V equals IR. That's a voltage and current and resistance. But it goes beyond that. And so I actually had a list of all these things that were very, very similar at the time. I thought, gosh, there's got to be something to this. They've got to be able to map them. But of course, I finished school and went off and did my own thing. It took a while before I could had enough time to come back to that. And then it got worse, right? Then it just is more than just electronics. Studying quantum mechanics. It's okay. That's even trickier than electronics and very simple equations. Now you get really, really deep into probability and some incredibly long equations, and most people still don't even understand. And I thought that's probably where the problem is, right? It is really the universe have all these different set of laws, quantum mechanics, classical mechanics, or could it be simplified to really just be one and the same? And I know that the common wisdom right now is that anything smaller than the atom uses quantum mechanics and a separate set of laws, and everything larger than that uses another set of laws, Newton's equations, for example.
Did the engineering take you into quantum? I missed the leap there. Exactly. Did you have to take some basic quantum for your engineering degree, or
no?
You were
just basically electronics. It probably stopped at like Maxwell's laws, not getting into electron probability. That was all hobby. It came a little bit later. Curiosity.
Yeah, just curiosity. You just wanted to go a little bit deeper and understand what these equations were talking about.
Exactly. Yeah.
That's interesting. Yeah, because it is fascinating that the fundamentals of engineering come down to the atom. It's almost like the atom is the unspoken god of all of these. And then if you want to find out about the atom, you have to go to the quantum mechanicists. The quantum mechanics?
Yeah.
Okay. So something strange happens when you start looking at quantum, which is that you're told to abandon your intuitions about how the everyday world works, and you're looking at some pretty heavy math, maybe for the first time in an applied sense. You're very deep into differentials and more complex algebras. And yeah, that's usually where most people get off the bus.
Yeah, and this goes back to undergraduate, and I didn't do any of this work that we're going to be talking about, way back then in undergraduate work. But at that time, I remember sitting in one of my electrical engineering classes thinking, okay, electricity is just electrons flowing down a wire. And I was thinking to myself, okay, if I modeled this like Newton's, just pushing a boulder, very simple, mass times acceleration is the force. I thought to myself, couldn't we just model those electrons moving down a wire the same way? But again, we have to fast forward many, many years until I actually had the time to kind of sit down and try to solve that problem.
And but when you got to the point where you solved that problem, did you come to the same conclusion that it's not possible for electricity to be the flow of electrons
Oh,
down the
no,
wire?
no. Electricity certainly is the flow of electrons. I don't doubt that. No, I don't think most people will. It's just how to model that electrical flow. But more importantly, can you use classical mechanics, just like Newton's equations, to model that instead of maybe Maxwell's equations or Coulomb's law?
I
Well,
guess the reason we
there-
hesitate at the flow of electrons per se in terms of marbles as a model is that the speeds are very incompatible.
yeah,
Is that
like
what you're getting
the
at?
speed of propagation of the electron through the wire is like centimeters per second, but the speed of electricity is nearly the speed of light.
Yeah, true. True. Electrons move incredibly slow. And it's not like you're measuring an electron that flows all the way down a wire. It's not
Hmm.
one electron. One electron bounces kicks the next one off, et cetera, et cetera. And they're very, very slow. But it's that charge property that moves at the speed of light, right? Electron might be sorry, I'm going to have to describe this over a podcast instead of using my fingers. Apologies. But as that electron moves, it is incredibly slow, but it creates that electrical charge, a wave, depending on how you really want to visualize that, that's kicking off that next electron. That is at the speed of light. It's very fast.
It's the relay of the interaction that's traveling very
Well, the
fast.
charge property, right? And that's an
The
interesting.
property.
And so, do you have a physical model for charge?
Oh, we're getting in deep immediately.
I mean, we might as well, right?
Yes, and that's one of the first things is to solve what is charge. Because today, if we're trying to map those equations together, they don't map at all, right? I'll just pick on just the two of the equations I just mentioned, but there's many, many more than that. But if you look at voltage, voltage looks a lot like a force, right? I mean, if you're modeling an electric car, for example, you determine the voltage, then that's going to equal something that you can then translate into a mechanical energy and determine how fast that car
Like a
goes.
pressure or something.
Yeah, eventually it rolls up to a power. That's the easiest way to translate. But anyway, back to the question of what is charge. If you look at the units, they're very, very different, and that's why they're incompatible equations. Voltage is measured in volts, and force is measured in newtons. And a lot of these are named after people, right? Isaac Newton, of course, for force. Voltaire for volts. But the charge is measured after Coulomb. It's coulombs. And so if you can solve for that and figure out what is charge, and I just simply replaced it with the units of meters, which I realize doesn't make sense until I explain it, but a really, really simple trick, converting anything that you see with a C as a unit to meters allows all these equations now to be mapped together. And then the question is, well, what the heck is meters? Why would charge be in meters?
Can you elaborate?
Yeah, what the heck is with that?
I see it as a measurement of wave amplitude. Okay, so for example, charge, a positive charge and a positive charge can be constructive, meaning if you put two charges together in Coulomb's law, you call that two. If you're three of them that are positive, you do three, and that's how you do Coulomb's equation. So you might have three protons and one electron. So you literally say three charges of one and a minus one charge of the other. It's just it's constructive or destructive wave interference if you think about it. So if you think about charge in terms of it's a wave moving, and you call that your measurement of amplitude, a wave amplitude is a distance. Then what you can do is you can model that like a sine wave. The peak of that sine wave is a distance. Call it meters. And so when you have two sine waves that are constructive, it's double the amount, just like how charge is double the amount. If you have two properties that are opposite sine waves, it's called destructive interference. You can actually subtract one. It goes from 3 down to 2. So the same idea applies for wave amplitude as it does the same properties of charge.
We spend a lot of time thinking about what is the substance that's waving, right? Have you toyed with that idea at all? In these atoms, what is the material body that's waving?
Yeah, that's really, really good question. This is where it flies in the face of mainstream science, which is, the current wisdom is that space is empty. But with anything with waves, everything that we know about waves and everything larger than the atom, I should say, sound waves, it's air molecules that are vibrating, water waves, it's water molecules. Everything else that we know about has a medium.
Mm-hmm, mm-hmm.
So light, which is a wave, right? It has you can do different frequencies of wave. It's a transverse wave in the case of light. Electrical charge is maybe more a little bit different. It spreads out in 360 degrees, more like a sound wave, so it's more like a longitudinal wave.
Mhm.
But to your point, everything else has a medium. So
It's
what is the
almost a
medium?
verb, really. Wave is kind of a
Mhm.
verb. It needs something has to be waving for a wave to happen.
Something has to be waving. Yeah, I do believe that there is something there, that there is something to wave.
Mhm.
And what brought you to that conclusion? Because that's pretty starkly in the face of what one would call consensus quantum mechanics.
hmm just for the simple fact that in order to create a wave, something has to be waving. And then as you dive a little bit deeper and you say, okay, charge, everything sort of works out with electricity if you replace the units of coulombs with meters. And then what is meters? So it comes back to you can model charge as a distance from equilibrium, but there has to be something that is waving. So the other thing I think that sort of got me there is all of Planck's constants, including Planck length, which is very 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 small, 10 to the minus 35 meters, incredibly small. We'll never be able to see it, but just the fact that it shows up in equations and what is it, just leads me to believe that there is something incredibly small in space that is probably waving.
Yeah, I think you can learn a lot too by material analogs, especially the other day I started looking for where on Earth, where in our everyday reality would you see a transverse wave? And the only thing that I could come across is torsion. So transverse shear waves are torsion. Essentially, it's like twisting on something.
hmm
And so I think we can learn a lot about the medium eventually by examining the way that it deforms in these processes.
A torsion one is actually even more complex wave. It is a good example, but a really simple one to me is take a buoy in the middle of the ocean or just put it in a pool, do it up and down a certain frequency. That's going to create a transverse wave at the top
On the surface in only two dimensions. I
in
guess
only
it's
two dimensions.
yeah. So it's not quite as perfect. I just can't think of the way that you would deform a material transversely other than twisting on it.
hmm
Which is interesting because light only comes in one twist or the other, and so I don't know. It just it starts to add up to a picture of what is happening in this medium, and I think we can learn about I think we can learn about electrodynamics the same way.
Yeah.
Yeah, do you so if you have a meter model for charge, which is the waving of something, do you then relate it to light as well?
Yes, but the amplitude that I'm referring to is more like the longitudinal amplitude. So think about a sound wave first. It's the distance from equilibrium. You have to take the average of all molecules in a wavelength, and it's the average distance,
So,
from equilibrium.
so if I put this onto the atom, let's say we're talking about something that just has an S shell. I'm thinking of the displacement of the smallest size of the atom relative to the largest size. And so as it pumps,
hmm
is that a fair
Well,
approximation
electricity has
of
this weird thing where it twists around too, right? I think we can learn a lot about the motion of this wave in terms of the spin equation itself. Actually, well, not the equation, but the Dirac spin concept, which tells us about the way that this twist is happening. And so so yeah, while the atom is jumping between energy states, it's also got this particular rotational symmetry, which is very bizarre.
do you want to do you want to
Yeah, I think it's interesting. So if you try, I don't know if you've looked into the relation. Well, have you looked into the relationship between spin and charge at all? Because it's quite an interesting little puzzle. And you
Yeah,
go
they're
on
different.
you go on
Yeah.
Stack Exchange and you ask what's the relationship between spin and charge, and everybody's like nothing. And then you really start to think about it, and it's like, well, that doesn't totally make sense because obviously you have Lewis pairing and paramagnetism falls out of this at some point, and there's most elements they don't occur with unpaired electrons, and so they'll bond or they'll become ionized or something. And it seems like there must be a really tight relationship between spin and charge. And then if you think about the motion that the spin 1/2 tells us, this particular, it has to rotate twice before it gets back to its starting point. And, there's only a few ways to solve that materially.
Yeah, no, spin and charge are very different. If we model it, it's one is electrical force, one is a magnetic force, right? So when you're actually doing equations for it, Coulomb's law, electric force, you get to Maxwell's equations, and now you introduce magnetism in there, which is a spin property.
Yeah, but spin and or electricity and magnetism are twins in some sense.
Still based on the same particle.
But
Yeah.
so to for me to create a mental model of when you're talking about coulombs as a sine wave displacement, if you're talking about just a 1s shell, like Shila's trying to say that if you're looking at the spin of that 1s shell, it's probably not spherical. There's probably a toroidal involution.
Well, it's
that
one way to
relates-
solve it anyways that we've thought of.
Yeah, and then that way you relate the surface of the atom to what's happening at the nucleus, where you have an involution of the surface and a spin, and that motion probably also creates magnetism. But I'm just trying to model, let's just for now treat it as this 1s shell that's spherical. When you say that coulombs can be equivalent to meters, is it the displacement of that shell relative to the size of the atom, or what is the meter that we're talking about here?
Oh gosh, no. I'm not suggesting that it does eventually affect that shell, but no, that has nothing to do with what that orbital distance is. Actually, that's one of the topics I'd love to come back to today, but I think we have to take multiple steps to get there before
Yeah,
I
of
can
course.
explain that. But short answer is, I think there's many different wavelengths in there, right? You've got a wave that's flowing between that and the 1s shell. There's probably hundreds of thousands of tiny little waves. The displacement is basically for each wavelength. Right, what's the average distance from equilibrium that something travels to create that wavelength? But there's many wavelengths before you get to that where that 1s shell is.
I think the confusion is coming from what is the shape of this wave? Like, what is the material move? On an ocean, you have a wave that goes like this across the surface. But on an atom, are we talking about it's twisting and it's pushing? Because the voltage and charge seem like pressures from one atom to the next. You're putting some pressure. And so what is the shape of that pressure, I guess, is the question.
Well, charge is inherent to a molecule, right? Like electricity, you have to have a path.
Mm-hmm.
But charge we treat as being inherent to just one atom.
Particle, yeah, the particles in the atoms. Right, electron, a proton, has charge.
But the weird thing about that word particle that always comes up is that a particle isn't the same as a particle of dust. It's not a static body with a contour per se. It's given form through its motion, which is very interesting.
Yeah, so I think that's a good point, where one of the ways in which we've been recently conceiving of I hate to say the universe, but the universe is that there's an interconnection between all atoms, where if you have light is the product of the connection between atoms. If you have a one atom universe, you can't have light.
Mm-hmm.
You have to have at least two atoms in order for there to be something that is passed between them, and it is passed along the paths that link the atoms. So if you imagine that the atom has a radial architecture, for example, like an atom in a vacuum alone has a radial architecture. You have two atoms, let's say a two-atom universe, they both have radial architectures, and where they intersect is where you would have light travel between them.
Mm-hmm.
How does that sit with you?
No, I'd agree with it. But if our earlier conversation was about waves, I think of a charge. Charge is spherical, right? You take a proton and you can put that electron almost anywhere, and it's going to be attracted, right? So it's spherical in nature, and it declines at the square of distance. That's Coulomb's law. So I think of that as just longitudinal waves. A speaker in the middle of the room that vibrates air molecules, same thing. Or it's hard for people to imagine. So imagine now we're talking about a buoy on top of the water. Let's make it more 3D. Let's put a balloon in the middle of the water. Now it's in the middle of that pool, underwater now, right? And let's imagine waves that are first coming in and then bouncing out, right? That's the everything affects everything in the universe. So every particle in the universe has this property of charge, is sending out waves that affects others. Okay, so now imagine this balloon in the middle of the water, bouncing and reflecting those waves. That's going to come out as longitudinal waves.
Like if
Now,
the balloon's sort of breathing, if it's sort of
yeah, just imagine it's breathing, and in 360 degrees, every single direction, it's being reflected. Longitudinal, meaning longitudinal wave is the same direction of propagation for the wave. Okay, and that means when we're talking about amplitude, the amplitude is the same direction. A transverse wave is different. The amplitude is measured at a 90 degree, right? That's the equivalent of the balloon or the buoy moving up and down at the same time. A transverse wave has a very given direction. So now you put two of these underwater. If one is moving in the right direction, that's why light could be seen at the other balloon. But charge is a property that should always be occurring, no matter what, whatever vibration for that transverse wave.
the cool thing that we found about modeling at least the beyond the immediate shell of the atom as this radial structure is that you have individual radiations, these filamentary projections that are capable of conducting transverse waves because you can twist on them essentially.
Mm-hmm. Yeah, I'd love to, if you guys don't mind, I'd love to come back and explore the 1s shell. That's actually what I had in mind for today anyway.
We can play with that, yeah.
Yeah. So do you mind if I try to explain a classical approach to that electron's position in the 1s shell?
Oh, for sure.
Let's do that.
Tell us your thoughts.
Yeah, like I said, I want to do this in steps though, because I think the more important question to ask first before I explain the part 2 of this will be a classical approach to that position. But I think the natural question is going to be, okay, why now, right? There's a model already, a probability function. And since I'm tying this to classical mechanics, I actually want to start with history and go all the way back to 1600s. And again, I'm going to make this fast. I won't spend too much time.
No, take your time. Take your time. We're
in the beginning.
Yeah. So 1600s, Newton, right? That's classical mechanics and everything that I'll describe for the atom actually comes from Newton's work. So let's kind of step through a few centuries first, and then I'll explain why this is something that can really only be done over the last few years. So 1700s, because we were talking about Coulomb already and his law, and Coulomb's work is going to be incredibly important even in this classical mechanics. He did that. It's important to know that Coulomb did that even before knowing what an electron was. That was late 1700s, and the electron wasn't discovered until the late 1800s. Late 1800s is really the start of quantum, although 1920s is really more start of really quantum mechanics. But so electron discovered finally, late 1800s, but the proton in the early 1900s. And that's when for proton and electron, oh gosh, they don't collide together like you would expect. It takes an orbit. And that's what, at first Bohr thought, okay, it's going to look like a planet going around the sun, but it doesn't. It kind of goes in and out and has this probability function. And that was the birth of quantum mechanics. Okay, but at that point, the proton was thought to be this just independent particle. It has a positive charge, and electron has a negative. So still, even at that time, in the 1920s, when quantum mechanics was kind of born, they didn't have the knowledge that we have today about the proton being a composite particle, meaning that it's not a standalone particle. It's actually made of others. It actually took another 50 years, 1960s, until the proton was discovered to be a composite particle. And at that time, 3 quarks. That's actually still thought of to be 3 quarks. But it's 2015 that CERN, at higher energies now, finds the pentaquark model of the proton, right? And that's 4 quarks and 1 antiquark. Everything that I'll explain that my work has been done is based on that 2015 model of the proton as a pentaquark. So my reasoning is, in the 1920s, they wouldn't have had this information to do it. Even the late 1960s, when it was first discovered as a composite particle, you still couldn't have modeled it this way. So my point is, what I'm going to try to illustrate with a classical mechanics view of it can only have been done in the last 8 years since the discovery of the pentaquark.
That's cool, because we see this in science all the time, right? Where the world will almost have prepared the scene for new ideas to pop up, and then often multiple individuals will come up with the same or similar ideas at the same time. It's kind of uncanny when you think about it. Yeah.
You want me to go to the next step then?
Hit it, yeah.
Explain the idea. Okay. So in a pentaquark model of the proton, again, the key is that there is 1 antiquark and 4 quarks. Now you have to imagine what this looks like kind of assembled in a proton. But just keep that in mind that there's one antiquark. So back to classical mechanics. There's a rule in classical mechanics, which is called the sum of our forces rule, that something's at equilibrium when you have a force coming one direction, a force coming another direction, at the point where everything is equal, it stops. That's the stable position. Okay. And let's just get a visual of this first, right? If somebody's pushing on a ball, that ball is going to move. You have somebody pushing against that ball with the same force, right? They're going to have two sides pushing against each other, but it's going to stop at equilibrium. Sum of forces rule, classical mechanics. So I used that. I said, okay, let's apply. We know that the proton has a Coulomb's charge, and that's why the electron is attracted to it. So put a table and let's just imagine one colored, let's do a one colored marble red. Let's call that the proton. Let's call another colored marble blue, right? So you get a visual. You got two marbles on a table, red and blue, and they're attracted to each other. Now, if it helps, just think of them like magnets, although it's not magnetism. But if that helps, just think about a red and a blue marbles being attracted to each other, just like marbles would on a table. That's the Coulomb force. Now, what's important to know about that is in Coulomb's force is that the closer that they get, the stronger they're attracted at what's called the square of the distance rule. Same thing happens for gravity, by the way. It's a square of the distance, okay? So all that's known. Coulomb's law applies it here. But what's strange about that is that now imagine that same table, a blue marble and a red marble, they're attracted to each other, but right at the point where it gets close enough to, that blue marble gets close enough to that red marble, the proton, it doesn't collide. For some reason, it takes that orbit. It goes around that proton. And that's what a century ago Bohr was trying to model, and he came up with, oh, it's probably like the Earth going around the sun. But it's not. It's strange. And it's quantum mechanics. So now that's the first part. And I think that first part, even Bohr modeled. He understood what Coulomb's law was back then. Now let's take the one thing that we learned in 2015 about a pentaquark. Now let's just do another visual, right? Because you can do this at home. Do a dipole magnet, right? A dipole magnet has a plus and a minus side. Okay, let's put the plus side on my left, right? If you can imagine on the left side, and then the electron, that blue marble is going to be on the right hand side. So when you line up this, it looks like plus, minus, minus. When you take a dipole magnet, and then you take another magnet, what happens when you align something that is plus, minus, minus? It repels. And I think almost anybody, with a static magnet has seen this before. You flip it around the other way, it's going to be attractive. So imagine now a scenario where in a proton, you have that alignment, antiquark, quark, right? Plus, minus, and now the electron, let's put that also as minus. What happens in that case? It's repelling. And just like static magnets are different than Coulomb's law. It doesn't repel at the square of the distance. It's very, very strong up front, and then it decreases very quickly. It's known as the cube of distance rule. It applies to static magnets. I'm not talking about electromagnetism. So what happens now in our mental model of that dipole magnet, and again, I'm using a marble example, what happens as it gets closer, it's attracted until the point where it gets close enough, and then it repels. Again, because it's very, very strong up front. So what I did was I said, okay, I'm going to take this as the model, and I'm going to do the sum of forces rule. I'm going to calculate what that repelling force would be, and then I'm going to calculate what that attractive force would be. And just like two people pushing on both sides of a big ball, it's going to stop at some point where those forces are equal. And that repelling force, very, very interestingly, is based on the same strong force, which is about 137 times stronger than the electric force. The same thing appears in this repelling force equation. And strong force, by the way, is what holds the quarks of a proton together. And so simple math, I just did the repelling force equal to the attractive force. And for for helium atom, which is not helium, hydrogen, which is a very simple proton electron. Sure enough, it equals the Bohr radius. And what's the Bohr radius? That's the 1s position for hydrogen.
All right, so let me get this straight. You are saying that if plus and minus are opposite forces like push and pull, that in a classical system, you always have to balance these in order to attain equilibrium.
Hmm.
And so there's some sort of tensegrity occurring. Like the easiest way for me to think about this is like trying to aim a rifle or something. The you really want to apply if you hold well, forget about guns. Sorry, anti-gun people. If you take your hand and you try to hold it still in front of you, you can hold it pretty still, but it's still wiggling a little. If you push your hand against one another, you can hold it almost perfectly still. And so when you apply opposite pressures, you actually can stabilize something like a structure. And so what you've learned from balancing the forces in the atom is that there's some sort of structural element that emerges from this.
Yeah, yeah. So what you can do, and I did this for 20 different atoms, from hydrogen to calcium, and then the ionized versions of them as well, which totals up to be more than 400 calculations I did. You can use the same rule, which is you've got a push and a pull effect. And so where is that equilibrium? Where is that balance? Now, at this point, which still doesn't explain the probability. I'll have to come back to that in a second. But the work that I did, I said, okay, right where that we have that equilibrium, yeah, the electron's position is very strange. It comes in and it comes out. But the strange thing about atoms is that even though the electron has a probability, the spectral analysis, meaning the photons that are generated from it, is very exact, right? It assumes that electron for hydrogen is at that Bohr radius when you do the calculation for the photon energy. That it doesn't matter if the probability says it might be a little bit closer, or it might be a little bit further. So I took a lot of the spectral analysis and those photon energies, and I mapped it to the calculations that I was doing.
Can you relate this a little bit more to the pentaquark model?
Yep. Okay. So now, perfect. So the first thing to do was just to calculate where that equilibrium position was. But it still doesn't explain the strange nature of the electron being a little bit closer or a little bit further, right? The highest probable point is the Bohr radius for hydrogen, but that doesn't what it looks like though when you look at it. So now, in a four quark and one anti-quark model, how I modeled it for the geometry is I put the anti-quark in the middle, surrounded by there's four leftover, four quarks in the tetrahedral view. So now what do? You basically have the equivalent of four dipole magnets, right? You have the plus and the minus, minus, minus going all the way around. And remember, the proton is spinning. To your point earlier, it has this strange half spin. Well, what do you know? A tetrahedron can spin 2 times around before you get back to the original starting position because it's not a sphere. We'll come back to spin in a little bit, but I'm on probability. So remember that it's spinning around. So the electron at some point is going to align with those dipoles. It's going to be repelled. At other point, you have the gap as it's spinning, where it just has that attractive force with the anti-quark in the middle. It's going to be attractive, then it's going to hit one of those lines of axis where the dipoles, as it's spinning, is going to be pushed back out. It's going to come in, it's going to come out. So it can't explain the probability function. But again, I have to come back to the ionization energies. It's always, always equal. So those forces that it has on repelling versus the attractive is always the equilibrium point. And when you calculate the energy, that energy is always going to be the same thing.
Oh, and so you're modeling the anti-quark at the center and these 4 quarks on the outside as dipole magnets. So it's basically 4 dipole magnets, and the positive end is at the center and the negative end is on the outside. And so as this central object rotates in space, it's the electron that is distal is experiencing a different amount of repulsion or attraction. But we're not talking about what is the attraction and repulsion, because we're assigning it like positive and negative, but it doesn't. These are qualities that are atomic qualities, not subatomic qualities. And so, what is it that these things are standing in for? Do you know what I mean by that?
Sort of. But let me come back to, I just used basic Coulomb's law for that attractive property, and actually just used a magnetic charge for that repulsive property. So that part of the equations, I wouldn't say it's, again, I just did it as classical sum of all forces. I think what you're asking is, can I go a level deeper and try to explain why that Coulomb charge, why is it attracted? I think that probably goes back to, again, to what is waving, and that we started the conversation with what is charge. And I'll go back to, I think it's a wave, and I think it's based on the displacement of that wave, that amplitude difference. But I don't think that somebody has to subscribe to that view just to take a look at the equations and go, yeah, this is just classical equations modeling out the behavior of the electron.
100%. It's interesting how if you read Newton's original, really when he came up with the idea of force and mass, and people were playing with the idea of mass before in terms of weight, but he really refined it. And he takes quite a many words to lay this out, but he's essentially saying you have push and you have pull. And, you can only rationalize push and pull in a couple of ways. And so I think that the ultimate finish line is imagining how the stuff, the ur stuff, the fiber of the atoms, whatever this stuff is that's waving, how it's producing these pushes and pull at different parts of its structure. And I don't think anybody has the complete picture of that right now, but it's what it seems like all of this refined understanding is leading us towards.
Mm-hmm. Agreed.
So, yeah, what's next?
I think we've only just done the very simple atom, hydrogen, right? That only has one proton, one electron. I won't go deep into this, but it's worth explaining how to build up to the next ones and the work that I did. So we're going to have a hard time using that mental model of magnets, but let me try to do this. Now let's imagine two dipole magnets in there, spinning opposite directions. That's essentially what helium is, right? You got two protons with spin up, spin down, so they're spinning the opposite directions, and now you attract two electrons. And so I use the same model as before, which is you have an attractive and a repulsive force. But the problem as you get to helium and beyond is now you've got more electrons. And so you have to now calculate an additional repulsive force, meaning that other electron a second electron has an effect on the first. So the equations actually get steadily worse, or more, I should say, harder, as we increase the number of protons and electrons in an atom. And for that reason, I actually stopped at calcium, which is element number 20. It started to get incredibly difficult. The other challenge is once you start building this out is that, as soon as you get to lithium, which is element number 3, it's the first time you have the beyond the 1s shell. You have the 2s shell, which means you have a different orbital distance. And so when you have different distances, you have to use what's called multiple equations. You have to solve them simultaneously to be able to do that. That became very, very tricky. And basically what I did, my work was writing all this out into about as simple terms as I could, so that I could put it into a program. I used MathCAD, but anybody could use whatever computer program that they want to solve multi simultaneously equations. And so anyway, so the point is I was able to solve for orbital distances from hydrogen to calcium, 1 through 20, and for the different shells that they have, the different orbitals that they have as well. And I posted that in a paper. It's all online as well. If somebody wants to kind of follow the math, you can see that I've calculated orbital distances. And then I took that a step further and I did the photon energies as well, because that's a little bit easier to match against experimental results.
And were you coming up with architectures for these shells? Was that the end result of distances?
I came up with a proposed architecture for the nucleus of the atom. How the protons in particular, I didn't model with the neutrons, because as I was doing this work, I realized it's really only the protons that affect the shells. I mean, you can add as many neutrons as you want; it doesn't really affect it. But I was coming up with proposed structures for how the protons align in an atom, because it directly affects, one, the orbital distance calculations, and then two, the strange shapes of some of these orbitals.
Yeah. Can you explain that? How the strange shapes start to emerge?
Yeah, to do that, I have to start first with, why does it jump from 1s to 2s, and then I can answer that one. So I'm going to do it in sequence. So we mentioned, we just did the model of helium, right? Helium has two protons. One spins up, one spins down. As soon as you add lithium, now you've got 3 protons. You've got 2 that are same spin direction, 1 that's opposite spin. So as I started to model potential geometry of what that nucleus looks like, I realized that every time you have a same spin proton, you're now increasing that repulsive force. Okay, remember you got attractive and repulsive. And so now we have a third electron that has a stronger repulsive force only where you have that axis where the 2 same spin protons are aligning. And I can carry this on and on as we go into other atoms. And so basically, I was building out a tetrahedron. So the first 4 protons are basically your 1s and your 2s. And now you get to basically a 2-level tetrahedron. So if you think about stacking a bunch of marbles in a tetrahedron, 4 is a 2-level tetrahedron. And then it jumps to the p shell. What is p shell? There's 6 electrons. And if you look at a tetrahedral stacking, a 3-level tetrahedron has 6. Basically look at third row is 6 places for 6 protons. If you continue to map that out now, what is D? D is like a 4-level tetrahedron, 10. What's the number for a 5-level tetrahedron when you stack everything together? 15. 15 is a little bit of a weird one because it's an odd number, but if you actually look at the periodic table, F orbital has the F1 has 15, but it's actually 14 orbitals. Really, really strange on how that works. But if you look at the atomic mass, it's because it can take a neutron from the d orbital. I'm probably getting a little bit too deep there.
Can I ask a question? Just a clarifying question. It seems like you're saying the nucleus and the structure of the nucleus and the structure of the shell are deeply related.
Deeply related, and you summarized it a lot quicker than where I was going with it. But thanks for summarizing it. Yeah.
And is that because the surface of the atom, the electron, is spending some time near the nucleus, and they're somehow continuous across that? How, like, is there some clue about how the nucleus is connected to the shell in this?
Yeah, they're absolutely connected. So in the model that I have, every time that I saw same spin protons in alignment, this is the hard part, is I had to come up with a proposed geometry for that nucleus. Every time there are 2 or 3 protons or 4 in alignment, it's basically creating the 1s or the 2s or the 3 orbital, because the repulsive force gets larger when you put these protons, same spin protons, in alignment. Now back to the strange shapes of the P, which is a clover shape, or the D or the F, which gets even more confusing. I then realized when you put together, let's just say you've got a 3-level tetrahedron, which means at some point you're going to have 3 protons in alignment. I realized that when you have, let's say 2 protons that are the same spin and 1 that are opposite spin, I realized that it could create like this clover shape. Why? Because most of the times as the atom is rotating, the nucleus is rotating, it's probably only pushing it out to that 2 orbital, second orbital. But there's certain points now where that opposite spin proton is aligning, where it actually kind of pushes out to the third one. So now imagine take a 1s, a 1s or a 2s sphere, and imagine just at some points where it's rotating, that it might, it's called 0 and 180 degrees. It might be aligning so that it's now 3 times that effect. Again, I model it classically as repulsive. What it's doing is kicking out every electron just in that axis.
So you're getting little bubbles almost popping out.
You get the dumbbell shape of the p orbital, and you do enough of them, you get the clover shape.
That's beautiful. I like that.
But the F orbital is kind of a weird one, right? Because it's got the dumbbell, and then it's kind of got a ring.
Yeah, it has a ring. So if you think about this, is coming back to the tetrahedron, and actually the D has this as well. The D also has 1 ring. So I know it's going to be really hard to explain on a podcast, but if you look at a stacking of a tetrahedron in the 3-level, which is a 6 for the P,
So
there's nothing.
Hold on 1 second. Let's this 3-level and this. Can you give a physical?
Yeah. So okay, let's take marbles again.
Okay.
Put 1 marble on the table. That's it's not even a tetrahedron yet. It's just 1 marble. Take that marble and put 3 underneath it, and then put that single marble on top. Now you're up to 4 total marbles, and that's considered a 2-level tetrahedron. You got 2 levels. Now raise that up 1 more time, and you to continue building out that tetrahedron as you're stacking marbles. There's a place for 6 of them. So 1, 3, 6 so far. That's a 3-level tetrahedron. If you continue, you do that, you raise it one more to a 4-level tetrahedron. The next number of marbles that it takes to complete it is 10, right? Which is the exact same as what the d orbital has. Okay, but if you take it now from the bottom, when you look at the p orbital, there's nothing in the center. Still, everything is around the edges. When you do a d orbital, it's the first time that you have something that's just dead center. Okay, just one marble. When you do the f, everything's around the edges except for three marbles. Again, you have to take this and look from the very, very bottom. That just so happens to be, the D has one of these rings and F has 3 rings. It's the exact same as being in the middle of that tetrahedron.
Have you heard of the key cyclist guys? We've had a few of them on the show lately. No, they're really hot on this tetrahedral architecture as well. I think you guys have stumbled upon a similar understanding. You got to check these guys out. Maybe we can put you in touch.
Yeah, I should be fair to people that have done all the work before. There's something called VSEPR that has modeled a lot of the atoms and using tetrahedral structures. I borrowed from that. Of course, they don't have the idea of protons in alignment as a repulsive effect, but to make things a little bit faster, for me trying to do a model, I borrowed off of VSEPR.
Well, yeah, that's how science works. You got to take the best ideas and put them all together. I mean, one thing that they're really working on, it seems like, is the complexity that emerges. We understand that in reality, elements are found in these complex configurations. There's hybridization, which is really a pretty basic chemistry principle, but normally when physicists think about the atom, they're just thinking of these overtones of hydrogen, essentially. And so, yeah, I think there's a lot of tetrahedrons popping out in the way that these orbitals hybridize as they start to interact with others.
Mm-hmm. Yep. And going back to your point earlier about spin 1/2, which is a 720-degree rotation, you take a tetrahedron, spin it like the right way. You have to spin it so that imagine the pointed top at top. Imagine spinning it once where the pointed end is down, and then spinning again with the pointed end is top. So you can. I've actually done this in a computer simulation using Blender. You can get it to spin in a 720-degree or 1/2.
Mm-hmm. Yeah, that's really interesting, especially for the nucleus, because the model that we're working under right now is something like the shell is involuting in a way to accomplish this spin 1/2, but the nucleus has been a bit of a mystery to us still. So I'm really thinking about that a lot. It's really interesting.
Yeah, and I'm also a firm believer that nature just expands on itself. So the proton happens to have this shape. That's how the nucleus is also arranged. Remember, we're talking about four quarks and antiquark in the proton, and then if the nucleus builds on that same shape, you also see it a lot in molecules. And so I think it's just nature expanding on itself.
That makes a lot of sense. I think we do see, this is one thing that absolutely spooked me out when I was starting to study more complex physics. My PhD, I was studying a lot of transport behavior, particularly water evaporation. And I just realized one day that all these transport phenomena had the same basic structure, heat flow, fluid flow, to some extent conductivity. And it's wild when you start to see how conservative nature is really with her behaviors.
Yeah.
Patterns.
Yeah. And if we can just kind of get through all the mess, we realize that it really is simple.
I think it can be. Yeah. We've gotten ourselves in quite the mire, though. I mean, a lot of it seems to come back to, physics is such a mathematical discipline. It's very easy, and other people have made their careers on this idea that physics has gotten lost in the math, and it's very far removed from this physical understanding, this material conception of what's happening. Even as we sit here and try to rationalize push and pull at the atomic level, it's tricky because it hasn't really been a consideration for a lot of the people institutionally working at the front of that. They're perfectly happy to look at the equations and model it quantitatively, and there's a lot of structural catch-up work to be done, I suppose.
Mm-hmm. Yeah, agreed.
Which is cool if you're interested in that kind of thing.
I'm looking. I'm still trying to visualize the way that these are organized, and when you're talking about the bottom view and the side view, and I pulled up the energywavetheory.com where you have this is your site, right?
Yeah, it is. Yeah.
Okay, and so I'm starting to get a better sense of it, and so
Yeah, we'll put that in the description.
I'll put it in the description. I
Yeah,
mean,
what might be better is I'll give you a link to a paper. I literally just posted a paper yesterday that explains all of this. It's actually a paper I did a few years ago, but I simplified it a little bit more. Prior work, we talked a lot about the waves and trying to model amplitude. I developed a lot of my own constants for it, and I realized that might be more complex. So I simplified the paper to just use classical constants that people already know: the electron's classical radius, electron's rest energy, the fine structure constant. So I cleaned up that paper and posted things that people would recognize, and I just put that up yesterday, and also I'll send you that link. I think it should explain everything we talked about today.
Do you have a sense of how this is going to impact people's lives? That's, I know, a really hard question, but it seems to me, I mean, I can answer this question, but oftentimes it seems like people can't grasp how fundamental physics would ever matter to them.
That is a very good question. Since I'm not in academia, I think about this a lot, which is when science comes up with something, can you build a product? Can you build a business out of something that can impact people in a meaningful way? I still struggle with, all right, understanding quantum leads to what? I don't know. But I do think about this all the time, and the one thing that I'd love to do is figure out gravity, because I think there's a lot of potential applications that we could just do a lot better once we understand gravity.
Mm.
I don't know what that answer is, but that's why I do spend a bit of time trying to think about that and how to productize something eventually.
It seems like if we're going to explore other star systems, strapping a bunch of burning stuff to our backs and flying through the space is maybe not tenable in the long run. And if we could figure out how to manipulate gravity, we'd be in a whole different world.
Yeah, yeah. I'm in the same belief. I just don't know the answer to that.
I mean, it seems like fusion too. What were you going to say?
I was just going to say, in terms of reimagining quantum mechanics as being something that actually falls out of classical mechanics, does it change the way that you would design and build electronics?
I don't think so. Again, because I've spent a lot of time in the electronics industry, working on wireless and cell phones. I still think at the end of the day, the engineers are going to be using Maxwell's equations. I don't think that changes anything.
And that's what's so crazy about the difference between science and engineering, is that for engineering, you need a diagram of the useful variables, and that's it. But science is asking a whole different set of questions of what's going on fundamentally.
Mm-hmm.
I was going to say fusion too. I feel like understanding the atom is critical to being able to pull off this fusion magic show that everybody's absolutely desperate to see pulled off. And a lot of our fusion trajectories right now are based on trying to rebuild a star essentially inside of the laboratory. And it seems like if we don't understand the atom, then we probably don't understand stars, and it might be holding us back in some sense, which is maybe a hopeful point here, that really getting a structural layout for the atom in terms of what these forces are, what's actually happening, who's pushing on who and who's pulling on who. We might be able to manipulate that in a really interesting way.
Yeah, could lead us down a really interesting path. I agree.
Are you collaborating with anyone on this work, or are you mostly focused yourself on it?
No, I've had collaborators on different pieces of the work. In fact, even this one that we've just referred to, worked with two other collaborators on it. I've had the help of people working on projects that I'm on, and I certainly have built upon the foundations of others too, right? And I always give credit where credit is due.
Yeah, shout out to Chris, who brought you to our attention. He's been
Chris
around.
Seeley.
Yeah, Chris Seeley. He's been around the community for a while. He's a man full of ideas.
When you talk to other people about this, like you have this well laid out theory. It's geometric. It checks all the boxes, and you go and you present it to somebody who is maybe more into the probabilistic, spooky quantum mechanics side of things. What's their reaction like?
I'll be honest, I haven't really spent a lot of time presenting it to people that are down that path. I post the website you referred to earlier. Posted a lot there. Actually, the website gets a lot of users. I think there's about 500 or 600 users per day. So I'm happy with the attraction that's gone. I post a lot on YouTube. To very visual, right? I always that's the hard thing about podcasts. I keep talking about. Imagine this, imagine that. I'm very visual. The things I post in video format, just a little bit easier. So I like to post there, but. I just put out there, and yeah, unfortunately, get a lot of comments from people. But no, I don't spend the time selecting people to say I'm trying to convince you of this.
Yeah, there's a lot of wisdom in not trying to explain things to people who don't care or aren't interested in that and looking for alternative ways of thinking about it. It's kind of it's both morally painful and it's like demoralizing, I guess. Sorry, demoralizing, but it's also a kind of waste of time too.
Well, I wonder because I mean, there is some utility in presenting it to somebody who thinks deeply about it from a different perspective, because they can come in and they can point to things that aren't in alignment with the, let's say, experimental data or something like that. And I'm not saying that I expect you to go and proselytize to quantum mechanicists, but I do wonder, just because we have a lot of friends that are working on things that are kind of on the outside of consensus, and they have they universally have a very strange experience where people behind closed doors will agree with them, and they will say they're onto something and be very positive about the work, but they will also have this perspective that, well, I can't really say anything in public because it's just too dicey and too difficult to come out on the side of something that works against consensus.
Oh, I've heard the same feedback. Yeah.
And what do you give much time to thinking about why people are so attracted to the quantum models in their current spooky form?
Oh, I think again, it goes back. That's why I want to start with the history. I think, given the time frame, if you're in the 1920s and you're working on these models, you go with what you know, right? And you have to explain the electron's strange orbit. But again, I think of those same people that worked on quantum mechanics in the 1920s were around today. If there wasn't the legacy of saying you have to build on this, I do think those same smart people, if they recognize, if they were given the model of the proton as a pentaquark, I think they would come up with a model like I described today as classical.
Yeah, but the public really loves this spooky, weird stuff, though. They really like the probabilistic, almost deterministic aspect of it. It seems like I wonder if they had access to new information, how it would have been spun, because people want their superstitions so badly, and I feel like I'm always breaking hearts when I teach physics or something and or astronomy, and people want those magical experiences. I don't know if the human can let go of it, especially since the death of, well, not the death, but the decline of religion in the West, and people don't have that same authority structure, so they look to science. And they're like, isn't the magic in the atom, maybe? Or the stars?
Yeah.
What are you working on next? So you have this laid out. You said that you've worked it upwards through calcium?
Yeah, I stopped there. I started to run into problems as soon as I got into beyond calcium is the d orbital. That's where I began running into issues. Quite frankly, I haven't spent much time on it over the last few years, really. Now, other things have had me kind of tied up, launching a new business. So I do hope to get back to it one day.
Have you thought about light at all? So this electron is, we have the interaction, the production of light through the electron, essentially. And so we were talking earlier about the balloon underwater that's expanding and contracting, and it's giving out these transverse waves in all directions. And have you thought any about that problem exactly? How the electron is related to light?
Oh yeah, well, electromagnetic waves in general is something that for many years I actually have worked on because I'm in the wireless business and it's a lot of radio waves at different frequencies. So I give a lot of thought to that, and light is just just a different frequency in the EM spectrum. Um, I see it, right. We know that light, photons, is really a short packet, right? That was learned, long ago, and that was even a problem that Einstein was working on, right? Photoelectric effect. So we know that they're little short bursts, and we know that electrons, when they're captured by an atom, they can release these photons. Or the reverse is when you inject a photon, you can eject that electron. This is a reverse process. So I think your question is, well, how do I think of it? I think of it like an electron just vibrating until it's in place, right? It's very, very short. There, it's reaches the equilibrium. While it's doing that, it creates a transverse wave. That's how I think of it.
It's like a relaxation process or something like that.
Do you think much about cosmological questions?
Not very often, no. I through YouTube and other channels, I get a lot of cosmology questions. I typically deflect them because all the work that I did was basically atom or smaller.
Mm-hmm.
Yeah, it's interesting that cosmology is even in the world of science. It's been maybe it's one of the oldest practices is cosmology. When you look back over thousands of years, everybody's very cosmologically concerned, and then only in the last 50 years has cosmology actually been considered a hard science. It's very strange.
Yeah.
In your work designing wireless antennas and wireless communication technology, have you come across anything that struck you as very strange from an engineering and a physics standpoint?
Oh yeah, so we were just talking about how light and most of these are just little short bursts, right? That's again photoelectric effect. There are all sorts of things where it's a gas. The photon has to have a start and end point. Is very, very short. There are some strange things, about radio waves where it looks continuous and it doesn't look like a short little packet. And so that I think still takes an explanation as to why.
Can you elaborate on the difference there?
Yeah, so just imagine, light just looks like a continuous stream of photons, right? Yeah, it looks like it's hitting us all the time, but in reality, it's a bunch of little photons, all the same frequency that's hitting our eyes or whatever. But a continuous wave, and a continuous wave is something that just might be going on for a long time. So some of the radio waves that we work on from antennas are actually strangely a continuous wave.
Does that have more? I mean, does that have more to do with the way that those waves are produced as a product of a larger body that's moving, as opposed to this very, very small electron that's settling into equilibrium?
Yeah, probably. I don't think I know the answer to that one, but I think you're going down the right path, though, I think.
Interesting.
Yeah, because radio waves and radio antennas are really fascinating because the wavelength depends very much on the geometry of the superstructure, which I've always been curious about but haven't had the time to really investigate. But it seems like those atoms are certainly all working together. And even if you think about the way that radio waves will, we would say, travel through walls or something, right? But it's almost like they're using the walls to relay themselves. These large structures are capable of producing large wavelengths. It's interesting.
Do you have any sort of summarizing or closing thoughts on the work that you've done and the future direction and how you wish that people would contribute to it?
Yeah, I just hope that we can get to simpler science, and I do believe that the universe operates in one set of laws. Maybe to your point earlier, all the people that love this idea of probability, uh, but I think it's simpler than that, and I do think that at the end we can model even particles with classical mechanics.
I love that.
God does not play dice with the universe.
I mean, I really appreciate how much work you've put into this, and everyone should check out the energy wave theory because the visuals are beautiful. It's really high quality work, and I think that that's kind of what's necessary to shift things into a new mode of thought, because there's a certain level of quality that people expect from science, and that is in some ways a hindrance because you'd like to just be able to go out into the world and objectively discuss ideas, but we're trained on ideas worth listening to being ensconced in journals like Nature and Science and Cell, and there's a level of presentation there that, for me personally, I think that that's what grad school was about. It was about training you to talk at the level that is expected for a scientific idea. And I feel like the visuals that you produce are done to that level. And I think that that goes a long way towards making it something that people can kind of relax into, as opposed to being tense about, where is this taking me?
Oh, good. Appreciate that feedback. The other thing I want to do is I'll drop you the link for this paper that I referred to. Again, I just cleaned it up, just as of yesterday, knowing we're going to have this call. And that's more of the content that we talked about today. So rather than somebody getting lost on the website, which has a lot of other topics we didn't discuss today, it's very focused on how to calculate that electron's basically equilibrium point, and then the shapes of the atoms and those orbitals we discussed. So that I've summarized that in the paper, and I'll send you that link.
Excellent.
Nice.
We'll put it in the description.
Yeah, great.
Cool, man. Well, it's really good to meet you today, and I hope we can meet up again.
Yeah, likewise.
Yeah.
Guys,
Have a great
take care.
rest of your day.
Have a great rest of your day.
Okay.
See ya.
Bye.
Bye-bye.